Hi, this is Math 8, Unit 5, Lesson 7, Connecting Representations of Functions. So we're going to connect tables, equations, graphs, and stories of functions all together in today's lesson. So first we begin with an equation here, y equals 2x. We have a graph right there, and we have a table right there. Those are our three things we're comparing here. And it says here are three different ways of representing functions. How are they alike, and how are they different? Okay. So when we look at the first one, we have y equals 2x. We could use this, for example, to create a little table, right? We could plug some values in, x and y, and see what you get. So if x was 0, that would become a 0. If x was 1, 1 times 2 is 2. If x was 2, you get a 4. If x was 3, you get a 6. And we could create a little table like that. That table could then be used to generate some points if we chose to. Right, if we want to make a graph from that equation. And what we notice here is I have points 0, 0, 1, 2, and I have 2, even 4 right there as well. So one thing I notice is that this equation seems to match that graph pretty well. This graph is using a and b, but really this a is the same as the x, and the b is the same as the y. So these two things seem to be the same. This is an equation, and that's a graph of the equation, so they are very much alike, just different representation of the same function. When I look down here at this chart, though, notice that when x is 0, y is 0, or PQ, that seems to match our graph up there, but when I put the value of 1 in, I end up with a negative 2. So that's a little different. When I put 1 in over here, I end up with a negative 2, and 2 becomes a negative 4. Right, and over here negative 1 is a positive 2, and so I end up with a graph that, yes, it does go through the origin, that's the same there, but in terms of the graph itself, it's not the same. So this is actually the opposite in some ways of this equation and this graph in terms of just the way it looks. Right, the line is reflected over the y-axis, so it's flipping over here, which moves the whole thing. So it's not going to be the same. So we can look at the values and recognize that it's a different function altogether. Yeah, it's a function, but it's not going along with those ones there, and that's okay. Let's look at the next section, 7.2, comparing temperatures. Here it says this graph shows the temperature between noon and midnight of city A on a certain day. So this is city A's graph. This table here shows the temperature T in degrees Fahrenheit for H hours in city B. So this is city B and this is city A. Those are our two things we're looking at. One is in a graph form, one is in a table form. And now using that information, we're going to then do some comparisons. So which city was warmer at 4 o'clock p.m.? Okay, so let's take a look here. For city A, at 4 o'clock, we go up here and we see the temperature is about a little more than 57 degrees, but for now we can say 57 degrees. And on our table for B, at 4 o'clock, the temperature was 62 degrees. So which one's warmer? We would say city B. Which city had a bigger change in temperature between 1 and 5 p.m.? Okay, well here's 1 o'clock p.m. in city A, and here's 5 o'clock. So this temperature change is going from here to here, so how much is that? Here we're about 50.5, and up here we're about 58. So if we were to subtract that, we would see the difference is going to be, in this case here, about 7.5. So in A, the difference is about 7.5 degrees, and in B, going from 1 to 5, we're going from 82 to 58 degrees. We're going to find that difference, and that difference is 24 degrees. So which one had the bigger change in temperature? We would say B had the greater change in temperature with a 24 degree shift. Number 3 asks, how much greater was the highest recorded temperature in C than the one in A during the time? So we're going to compare the highs of B and the high of A. Well, the high in A is right here at about 59 degrees. Okay, so A's high is 59 degrees. B's high, we look at our table, we have 82. Yep, that's our biggest one, 82. So the difference is going to be what we're looking for there, 82 minus 59. And so we'll do some borrowing, and we end up with 23 degrees is the difference between the two highs. And finally, number 4, compare the outputs of the functions when the input is 3. So let's take a look here. For A, when you look at 3, we're right here at this point, maybe about 54.5 degrees. And for B, when the input is 3, we're here at 75 degrees. So that's our comparison between those two, and that's what they look like. In terms of the difference, we could do that. Oops, 54.5. And we see that it's about 20.5 degrees warmer in city B. And that's our difference between those two high temperatures. All right, and that's, oh, didn't quite get it there, sorry. So A is 54.5, B 75 degrees, and that's our difference there. All right, let's look at the next section. The next section says it's called comparing volumes, and so they give you we begin with the formula for the volume of a cube, which is volume equals S cubed here. And then they give us this little chart that shows the volume of a sphere, okay, which is a function of its radius, and the graph is shown here. So it does have this kind of curved line here, once again, like volume for other things, but look at the number differences. It's a lot different. Here's a 50 and 100 and 150 instead of just like little numbers. They're pretty big. So let's take a look at the first question then. It asks, is the volume of a cube with edge length S equals 3 greater or less than the volume of a sphere with a radius of 3? All right. Well, for a cube, if it has an edge length of 3, that's going to be 3 cubed. Well, 3 times 3 is 9, right? That becomes 3 times 3 times 3. 3 times 3 is 9, times 3 is 27. That's the volume of a cube. But how about the sphere? Okay, this is our cube one. And our sphere, though, when it has a radius of 3, we look at our chart here, and here's a radius of 3. We move up, we find the point, we look across to see what's the value of that point, and we see that we're between 100 and 125, so probably about 112, right? Maybe about that. So which one has the greater volume? Definitely the sphere with 112, whatever it's going to be, cubic centimeters there, compared to 27. If a sphere has the same volume as a cube with an edge length of 5, estimate the radius of the sphere. Okay, so if the edge length of 5, we'll go back to our cube. We're going to do 5 cubed to find out what the volume of that cube is going to be. That's going to be 5 times 5 times 5, which is 125. And we're saying there's a sphere that has that same volume of 125. So what would be the radius? What radius would get you 125 for the sphere? So in this case, we're going to go to the point in our graph of 125 and move across and find that point there, and then look down to figure out what would be the radius. It'd be right about there. What is that radius? Well, this point here is 3.25, so we're kind of between 3 and 3.25. So maybe we would say something like, I don't know, 3.1, okay, or 3. I don't know, hard to say. If that's 3.25, that's somewhere between 3.1 something, maybe 3.15. I don't know. Just making up something. So somewhere around 3.1-ish. Okay? So it's, again, it's an approximate. Compare the outputs of the two volume functions when the inputs are 2. Okay, so for a cube, if the input is 2, it's 2 cubed, which is 2 times 2 times 2, which is 8. For the sphere, if its input is going to be 2, then we look at our chart and we see where is it going to land at. Oh, I've been writing all down here, can't see. Goodness gracious, so sorry. Oh goodness, so sorry about that. Alright, so compare the outputs of two volumes. So for the cubed, it's 2 cubed, which becomes 8. The sphere, we look at 2 and we move up and we find the point there, moving across, and that's going to be, this is 25, so it's between 25 and 50, so maybe about 37. And that becomes our comparison there. Sorry I ran those off the edge there for you. So you can take a look at the notes there for how I got what I was saying I was getting. I backed up a little bit so you can see there. Okay. All right, let's look at the next one. 7.4. All right. Elena's family is driving on the freeway at 55 miles per hour. Okay, so that's her rate. She's doing 55 miles every hour. Okay. Andre's family is driving the same freeway, but not at a constant speed. The table shows how far Andre's family has traveled in d miles every minute for 10 minutes. Notice this is doing minutes, okay? She's doing 55 miles per hour. So hard to compare hours and minutes unless you do some changes. So the first question is, how many miles per minute is 55 miles per hour? So to set this up, we have to kind of go back to what we did in 7th grade a little bit. So we take 55 miles, and this is 55 miles in 1 hour. That's what 55 miles per hour means. And we want to get this down into minutes, which means I need to get rid of the hours and turn it into minutes. So the one way we do that is we're going to multiply this by, we're going to set up a ratio for hours. Well, in 1 hour, there are 60 minutes. And what happens here when I multiply, because just the way it works, if I have 1 hour here, that can cancel the 1 hour there. And now I'm going to be left with, as I multiply across, 55 miles in 60 minutes. But I don't want to leave it like that because I want to get it in terms of miles per minute. Okay, because that's what I'm looking for, miles per minute. So 55 divided by 60 is actually 0.916, or we would have kind of round that up to 0.92 miles per minute. Okay, so a little bit of process there. So I know that Elena's family is going 0.92 miles per minute, which means I can now start comparing things. Now granted, his family is driving at a different rate, but notice here, in the first minute, he went 9 miles. So we can already see there's going to be a little difference here, right? That's a little bit faster than that first minute. So who traveled farther after 5 minutes? So let's do the 5-minute comparison first of all. So a 5-minute comparison. So for Elena, what we would do is we're going to do, she's doing 0.92, and she's going to do that for 5 minutes. So how far is she going to go in 5 minutes? 0.92 times 5 is 4.60. That's how many miles they're going to go. Now for the Andre, we just have to look at the chart. In 5 minutes, Andre has gone 5.1 miles, just based upon the chart. So who went further in 5 minutes? We would say Andre for the 5 minutes. But then we take a look at the 10 minutes. For 10 minutes, for Elena, we're going to still do 0.92 and multiply that by 10, and that gives us 9.2. And then for Andre, again, we look at the chart, and at 10 minutes, Andre is at 9.1. So who had gone farther in 10 minutes? In that case, we would say Elena had gone farther in 10 minutes. So there's a difference there. Her constant speed allowed her to eventually pass Andre because he was going at the same rate. She was going at the same rate the whole time. How long did it take Elena's family to travel as far as Andre's family had traveled after 8 minutes? So let's take a look there. Andre's family in 8 minutes went 7.4 miles. And that's Andre's family in 8 minutes. We want to find out how long will it take Elena's family to get that far. So think of it this way. The distance she's going to travel is going to be equal to the rate she's traveling at times the number of minutes we're talking about. Right? That's the formula we're using up here when we use 10 and 9. We want to find the distance. We want to find the minutes now, knowing that she has to go 7.4 miles, right? And she's going to do that at a rate of 0.92 miles per minute. We're solving for m. So to solve for m, I divide both sides by 0.92. And 7.4 divided by 9.2 is actually equal to 8.04. And that's going to be how many minutes it takes her family to get the same in 8 minutes, right? So Andre's family, Andre's family in 8 minutes went 7.4 miles, and for her, it took her 8.04 minutes to do that same distance. So it takes her a little bit longer to go the same distance Andre's family did, at least at that point. For both families, the distance in miles is a function of time in minutes. Compare the outputs of these functions when the input is 3. So we want to do both and do a comparison there. So Andre, pretty straightforward. When we're looking at Andre's value at 3, we come back up to our chart, and Andre's value at 3 is going to be 3.0 miles. That's pretty easy. And then for Elena, we would do the 0.92 times 3 to find out how far they went in 3 minutes there. And 0.92 times 3 is 2.76 miles. So within a 3 minute, when input's 3, Andre's gone further than Elena's family, but we know in the end, Elena's family gets there a little bit faster. Okay, so here's your summary for today. You kind of read through this, that functions are all about getting outputs from inputs. That's our key thing. And for each way representing a function, equation, graph, table, verbal description, we can determine the output for any given input. Okay, so that was the idea today. Let's take a moment to work on your homework and let's check it together. All right, so here is tonight's homework. Math 8, Unit 5, Lesson 7. The equation and tables represent two different functions. Use the equation b equals 4a minus 5 and the table with a and c to answer the questions. This table represents c as a function of a. Okay, when a equals -3, is b or c greater? Okay, let's figure this out. Well, for b, when we're looking at -3, all right, we would say b equals 4 times -3 minus 5. We're just using that equation there, and we're using the value of -3 for a. So this becomes -12 minus 5, which equals a -17. For c, right here, when a is equal to -3, c is equal to -20. So which one is greater? The greater value, be careful here, is actually -17, right? -17 is a larger value than -20 on the number line, right? So here's our number line, here's 0, -17 is here, and -20 is here. This is a larger value. So don't get hung up with a number, look at this, it's a sign, don't forget the sign. B, when c is 21, what is the value of a? Okay, well, when c is 21, the value of a is 5. And what is the value of b that goes with that value of a? So what they're saying is, all right, well, if that's the case there, then let's plug in 5 into that equation and see what b is. So 4 times 5 minus 5, which is 20 minus 5, which is 15. So when c is 21, a is 5, and when b is 15, a is 5. And that's the idea there. C, when a is 6, is b or c greater? Well, for that one, we'd have to take a look here. We're looking at the table. Do we have a value of 6? Where is 6 at? 6 would be here somewhere. We don't have a number, but we know it's between 21 and 19. Okay, so we're not really sure where that's going to be there. When we plug in for b, we could say 4 times 6 minus 5. That's 24 minus 5, which is 19, right? So 24 minus, 19. So the b one here, so with b, we're at about 19. For the c one, we are between 21 and 19, probably closer to 21. Okay, if we had to take a look at that, probably about 20, maybe about 20 for c, not really sure. So when is it greater? We would say that c is going to be greater. That's the first thing. We'd probably say c is going to be greater based upon what we can tell, but there may not be really enough information to really determine that. All right, we can't tell what 6 is based upon this. We have to do a little more work. It certainly looks like the c is going to be greater. That's our guess. And that's because 10 has a value of 19, which is already going to be what this one is. So C makes the most sense. So for what values of A do we know that C is greater than B? So what values do we know for sure that C is bigger than B? And in this case here, we would say that 0 would be 1, because 0 times 0 here is 7. When I put 0 up in this equation, I end up with -5. So 0 is definitely going to work. And the other one we know that's going to work is the value of 12. And that's because 12 here is 45, and that one's not going to quite be the same amount. Okay, that's going to be 43. So I know for certain that that's going to be the solution. 0 and 12 are definitely greater. Okay, now don't forget that C, the answer they're looking for, is that there's not enough info to really tell, even though we can use some logic to probably predict. Okay, number 2, match each functional rule with a value that could not be a possibility. So we're looking basically for a broken rule. The rule doesn't work, right? So for each value you can plug it in. If you could get a solution, then it works, it's fine. If it doesn't work, then we would say that's the answer. Kind of weird. So 3 divided by the input. So let's pretend the input was 3. If I did here, 3 divided by 3, that works, no problem. If I did, can I do 3 divided by 4? Yep. Can I do 3 divided by -4? Yes. Can I do 3 divided by 0? 3 divided by 0, I cannot do that. And so this one here, A, does not work for 0. Okay? It doesn't work there for us. So I can't use 0 there. I'd have to make a rule that says except for 0, don't use 0. B, we have 4, add 4 to the input, then divide this value into 3. Okay, so let's look at this one. 3 plus 4 is 7. 7 divided by 3, it works. Don't know what it is, but it works. 4 plus 4 is 8. Divided by 3, it works. -4 plus 4 is 0. Divide that by 3. 0. Let's see. Does that work? -4 plus 4 equals 0, and then divide it into 3. 0 divided by 3 is going to be 0. It doesn't really work, does it? So I end up with a 0 value. That's just not going to work too well. We'd say let's not use that one. And then this one, subtract 3 from the input and then divide it. So if I put 3 in there and -3, I'm at 0. And if I divide the value into 1, 0 divided by 1, I can't do that. So C is not going to work. It's a little strangely worded problem, but just kind of get used to that. Look at this carefully, which one could not work. Okay, next one. Elena and Lynn are training for a race. Elena runs at her constant speed of 7.5 miles per hour, and Lynn's recorded here. Paper over. So we know Elena is 7.5 miles per hour, and then here is Lynn's times there. Those are our 2 things we're looking at. Okay, who finished their mile first is the first question we have to answer. Okay, well, we know that for Lynn finished the mile in 9 minutes. Do we know about Elena? We don't know about Elena, so let's take a look at Elena. Elena is going 7.5 miles, right, per hour. Okay, so we want to find out how many miles per minute that is to make it in minutes here. We do what we did in our lesson before. We do 1 hour over 60 minutes, and that gets us 7.5 over 60, which becomes 0.125 miles per minute. And the question then is, how many minutes does it take her to run 1 mile? So we know that she's going to go 1 mile at a rate of 0.125, for we don't know how many minutes. That's what we're solving for. So we divide both sides by 0.125, and we find out that it takes Elena 8 minutes to run 1 mile. So who finished the mile first? That's going to be Elena, because it took her 8 minutes to run the 1 mile. So a couple extra steps there to figure that out. Okay, we know we were given 7.5 miles per hour, but you had to convert that into miles per minute, and then multiply, or then set that up as an equation to find out how long it takes her to run 1 mile there. This is a graph of Lynn's progress. Draw a graph to represent Elena's mile on the same axis. Okay, well what I did is I'd say, well, it took her 8 minutes to run 1 mile, which is right there. That's the distance right there. And so then we take the ruler and we start at 0 and we line up 0 to 8 because she's running at a constant rate there. We just simply connect the dots and we say from 0 to there. That's what Elena's look like right there. For these models, is distance a function of time? Is time a function of distance? Explain how you know. And in this case here, and I'll let you write down your explanation, we're going to say both because the time they ran, the distance they ran depends upon how long they were running for. Now, because everything only has one value each, we could actually flip those around and it would work just the same. Number 4, find a value of x that makes the equation true. So we want to see if we can figure out what works. So we have negative 2x plus 1 equals 9 minus 14x. So I'm going to first distribute that negative all the way through. So I end up with a positive 2x minus 1 equals 9 minus 14x. And I'm going to move things around a little bit here. I like to have positive with my variables, so I'm going to add 14x over here. That goes away, so I have 16x on this side. I'm going to add a 1, it's going to equal 10. Divide both sides by 16, so that x equals 10 over 16, which is also 5/8, right? To check my answer to see if it's right, what that means is take that value of x and plug it in there, and plug it in there, and see if the two sides actually equal one another. And I'll let you check that out to see if it is accurate or not, and show your teacher. Have a great day. We'll see you next time.